Today I'm going to talk about, we'll see, there's a few things we have to do in computer graphics. We have to figure out how to move things around in three-dimensional space, okay, and manipulate them. One of the most important things we have to do, and this is going to take me about 3 or 4 lectures to get there, one of the most important things we have to do is get what's called a camera transform. We have to figure out how to take a perspective picture of something in three-dimensional space, project it on a two-dimensional plane, okay, and which is going to be our screen in front of us. Right? We have to figure out how to do this with perspective and everything else, make it look right. And we're going to do something called a camera transform, right, over the next few days. Today I'm going to do 2D. I'm going to move things around in two-dimensional space just to kind of make it's easier, right, if I do it in 2D. And Friday I'll do 3D. 2D to 3D is a real easy jump once you get the idea. It's a real easy jump. And then we'll start manipulating cameras around and things like this. In this class, in computer graphics in general, we use what's called a pinhole camera. Anybody ever do a pinhole camera? Right, when they were kids? Right, they usually do this sometimes in elementary school and all. You take a box, right? You put a piece of film in the back of the box, put a little tiny pinhole in the front, okay, and then you uncover the pinhole for a few seconds and cover it back up, and then you run and take the film into your lab and process it. Okay, and your image, if you think about it for a bit, appears upside down and backwards on the film, okay, because of the light rays coming in through the pinhole. Pinhole camera. We do the same things in computer graphics. We use a pinhole camera, right? We don't use the lens camera. Lenses are bad, okay? Lenses are bad. They distort things, and distorting things makes it really hard to figure out what's going on. So we use a pinhole camera. And sometimes if you're an image processing guy, you kind of forget that you're really getting images back from real cameras, but you try to pretend it's a pinhole camera, okay? So pinhole camera is one thing, but what we'll try to do here is the key phrase I want you to get out of this lecture is, how do you move things around in 2- and 3-dimensional space? Matrices, okay? You move them with matrices. And it's real easy to start figuring these things out. We'll get a set of elementary matrices we can use. There's all kinds of them you can use. They all have a very nice specific form that we can exploit, okay? And we'll exploit these things over and over and over again. So keyword to come out of this lecture is matrices, right? That's how we move things around in 2- and 3-dimensional space. And gee, one of the huge surprises in computer graphics that came out of the 1970s was that we can do the camera transform also using matrices, okay? And that's what's cool, because once we can do these things, we can pile up all these matrices together, multiply them into one big matrix, and we have one big matrix that does everything for us, okay? So that's the whole strategy, matrices. And you'll see it's pretty fast. So if you remember, I'm going to have these little frames running around, right? These are little coordinate systems. They all have 3 vectors associated with them. Well, today they have 2 vectors. I'm going to do 2D today, okay? But they all have 3 vectors associated with them and an origin, okay? And you can kind of think of the pilot in the airplane that's flying around. He's got a little frame on him, right? There's all kinds of frames in our systems, okay? If I'm going to do real animation, anything that moves has a frame associated with it, okay? Anything that moves has a frame, and sometimes if you do human figures, it has multiple frames. Every body part has a frame, okay? And what we have to do is we have to figure out differences between all these frames, and how do you go from, if something has this coordinate in one frame, what's its coordinate over in this frame, okay? And what I want to get out of these next few lectures is matrices. That's how you do it. And that's why we build computer systems that multiply, especially 4x4 matrices, really well, okay? Because all these things can be related by matrices. So here we go. I'm going to do 2D today, okay? 3D next time, although it'll be easy once I get done with today. So I've got this frame, okay? It's got a vector, two vectors. Oh, let's call them something different. How about U and V? And it's got an origin called O, maybe, okay? And I've got this little frame. Normally all of us try to deal with a frame that the vector U is 1, 0, the vector V is 0, 1, right? And O is 0, 0, okay? We try to deal with these things, but it really doesn't matter. If I have a coordinate up here, right, a point up here, P, okay, or I'm going to call it XY, probably, eventually, okay, P. If I have a coordinate up here, P, I can write P, oh, let's don't do x, y yet, hang on. I can write P as x times u vector plus y times the v vector plus the origin, okay? Let me put vectors on top of my u and v for a second. I can always write P this way. There's some coordinates, x and y, that I can use with my two vectors, okay? Right? And add it to the origin to get to P, okay? And we usually call x and y the coordinates of P in this frame, okay? You can kind of see if u is 1, 0, right, and v is 0, 1, right, and this is 0, 0, then we get x, y out of this, okay? But this has to do with any frame. And I should say, frames don't always have to be perpendicular, right? We're going to write them most of the time so that they are. They don't always have to be perpendicular. They can be skewed somewhat, okay? As long as two of these vectors aren't the same or scalar versions of one another, we're okay, okay? Mostly I'm going to think of them as perpendicular, though. But they don't have to be, okay? You can do this type of thing with anything, okay? So there's another way to write P. And here's where we get to matrices right away. And I've done this kind of once before, showing you this. This is a common trick. This is a common trick that we do over and over and over again. We write something in a matrix form. Okay? We write something in a matrix form. And what most people in computer graphics always say when they first look at computer graphics, they first look at computer graphics books, is they say, you're writing a point P as x, y, but it's always got this 1. It's always got this 1 in there. Why is that 1 there? Right? Well, the 1 is there because it picks up the O, right? The origin. Okay? And if you remember from that very first lecture where I did points and vectors, right? This is a point. You always a point. You have to add a vector to a point, right? So we have to pick up this O, right, to get a point back. And so we're going to be dealing with this kind of characteristic form here of x, y, 1 for our points. Most of the time we drop this stuff, okay? And we kind of think of, you'll see me drop it today. It's kind of always there, right? But I'm going to drop it here to move things around a little bit. So I'm going to talk about the coordinates of a point being this. Remember, the 1 is here to pick up the origin, right? It's got to be there. We've got these frames flying all around, okay? And what I want to do is I want to start moving these folks around a bit, okay? And I'll start this really easy, okay? The first thing I'm going to do is translate something called translation. Okay? And this is something called translation. And what it does is if I've got this point here, say x, y, in three-dimensional space, I want to move it, translate it out here, right, to a point called, say, x plus a in y plus b. Okay? I want to translate it out. And this is one of the most important operations we'll use, you'll see. This one's used everywhere. It's called translation. We'll use it everywhere we can. But how do you do this how is this accomplished in a nice way? And so what we want is we want to take a point, x, y, z, 1, and we want to translate it, make it into a point x plus a, y plus b in 1. Okay? Remember, I've kind of got these other things out here, but I'm going to kind of forget them for a minute. How do you make this thing go? Well, you use a 3x3 matrix. Okay? And it looks like this. It takes a little experimenting. But if I look at this matrix, okay, notice this has A and B down here in the third row, okay? And I do this multiplication, right? You can multiply this out in your head. You get exactly what you hope you would. Oops. Like this, right? And we call this matrix here, this matrix, the translation matrix. It's called the translation matrix. It's got a few characteristics that we'll see. Number one, these matrices that I'm going to write down today are usually pretty sparse. Okay, they got sparse meaning they got lots of zeros in them. And that's one of the characteristics of these matrices as we go along. When we go up to 3D, they'll get even sparser. Okay, it's got a third column here that I'll mention, which is going to be always 0, 0, 1. Okay. Now, why is that third column always 0, 0, 1? Well, to start with this to this, you've got to preserve that 1, right? And you don't want to move that 1 at all. That's the one that picks up the origin in our original equation. Okay? So we don't want to move this. So our third column is always going to be 0, 0, 1. When we move up to 3D, our fourth column is always going to be 0, 0, 0, 1. Okay? Because we're always going to have this 1 out here to pick up the origin, okay, as we go along. And warning you what's coming, when we do the camera transform, we're going to start to play with this fourth column, okay, which means we're going to move up to 4D for a little bit. I'm going to do some 4D geometry for you, which, if that makes any sense. Let's see. We're going to do some 4D geometry, let's just say that. Okay, I'm going to draw some 4D pictures on the board and things like that. So we'll have fun with this. But here's the first one, right? This translation. And notice that this one, if I call this T of A comma B maybe, give it some notation here. If I call this matrix T of AB, right, this T, this is kind of an operator. It can work on any XY, right? It takes any XY, translates it A and B, right? Whatever A and B might happen to be. Okay? All right, number one. Here's scaling, which is number two. A nice little transformation. Now, in this one, I want to take a point here, XY, and I want to scale the coordinates of the point. So I want to move this thing out here maybe 2x and 3y. Okay, I want to scale this thing. When we move things around in 3 dimensions, when we move things around, we're going to have to translate them. Okay, we're going to have to scale them, make them bigger, make them smaller. Okay, we're going to scale things to fit them inside our screen when we take pictures. And we have to scale them, and we're going to rotate them too. Okay, we're going to rotate them in 3 dimensions, whatever that means. Okay, we're going to rotate them. So scaling is the next one, and it typically is something that looks like this. If you take xy and you add your 1, and you want to move this to ax and by and 1. And figuring out the matrix to do this one is easy. Figuring out the matrix to do this one is easy. X, Y, 1. And I think all the matrix is A, 0, 0, 0, B, 0, 0, 0, 1. And you get what you would expect. In this matrix, I'll call it S of AB, right? Which scales something by AB. This matrix does. Now, got to kind of be careful here. I always have students come into my office and say, hey, I've done all this project and I can't, all I get is this single dot in the middle of the screen. Okay? All I get is this single dot in the middle of the screen. Well, in the camera transform, there's going to be a scaling matrix component to it. Okay? And what happens if both A and B are 0? Okay? What happens is no matter what you scale, right, it ends up being 0, 0, 1 over here, right? And what happens is everything gets collapsed, of course. You're drawing your entire picture inside one little tiny dot on the screen, okay, called the origin, all right? And it all happens every quarter. Somebody says, all I'm doing is getting this one little dot in the middle of the screen. I can't figure it out, right? Well, you've got a scaling transform that has, right, some zeros in it somewhere. And we'll review this. There's some easy ways to do this. Now, this scaling thing isn't quite as easy as it seems, okay? If I had, suppose I had a unit square here, like this, all right? A square, and it's got 4 points here, like that. So this isn't the unit square, maybe 2 units on a side, the square 2 units on a side. And I wanted to make it a square 4 units on a side, right? What I would do is just take all the 4 corners of the square. Here's, say, 1, 0, 1, 1. Here's 1, minus 1. Here's minus 1, 1. And here's minus 1, minus 1. Take the 4 corners of this and multiply, you know, just plug these things in, run them through here with the 2's in here, right? So I scale it by 2, and, right, I get something that's twice as big, okay? And it works great. But suppose I had something where my square, 2 units on a side, is over here. All right, now I've got the 1 at 1, 1, and 3, 1, and 1, oops, 3, 3, and 1, 3, like this. Here's another same square, okay? And the trouble, and with scaling here, suppose I took this square and I did this with 2's in here, okay? Can you see that what would happen is this square would move out to be like this, right? See it? If I just multiplied all the coordinates naively by 2, right? And so the problem with the scaling transform is it moves things, okay? Unless they're around the origin. Okay? It moves things unless they're around the origin. So what we have to do is combine scaling. If we wanted to just double the size of this thing in place, typically what you would do is you would combine your scaling, which seems to do the right thing when the center of your object's at the origin. You would combine your scaling with the transform, okay? So here, if I took these things and I first said translate, I'm not going to write the matrix now. Translate by first minus 2, which gets the center, this would move the figure down to the origin. Then scale it by 2, 2. And then translate it back by 2, 2. See what I've done? First translated it to the origin, then scaled it, then translated it. Okay? And what would happen then is I would move this whole thing down to the origin. I would blow it up twice, and then I would move it back, and I would get the square looked like this. Okay? Different. But it would expand it around its origin. And this is typically the way we use our translates. Okay? We use them around the scale, and I'm going to do rotation in just a second. We use them around scale and rotation to move things around for us. The cool thing about this is that this is the matrix and this is the matrix like that. And we can multiply these all together into one matrix. Okay? Nicely, you can multiply them all together as 3 by 3 matrices into one matrix that does the job here. Okay? That's the beauty of using matrices here, is that you can multiply the matrices together, get one matrix that actually does your job. Okay? We will use this over and over and over and over and over again, the fact that we multiply all these matrices together. When I go up to 3D, these are all going to be 4 by 4 matrices. Okay? Notice all my matrices have this characteristic 0, 0, 1 in the right-hand column. Okay? And when I get done, this matrix will have 0, 0, 1 in the right-hand column. Okay? We'll all be done. So this is the way we use these guys, right? Scaling and translation. We use them in this way. Scaling we don't do too much, but we got to fit things in. Okay? And we use translation a lot, and we use rotation a lot, which I'll do now. Okay? Now rotation takes a little bit of work. Just a little bit of work. It takes a bigger picture probably too. Now if I have a point xy here, okay, what I want to do is I want to rotate this point, and my rotation is always going to be around the origin. I'm going to rotate things around the origin. Okay? And I'm going to do something called the left-hand rule. Okay? Now let's see. There's something computer graphics people tend to use three-dimensional coordinate systems that look like this. XY tends, if you can think of this as XY is in the blackboard, right, and Z comes out at you. Okay? There are also some people that use XY in the blackboard and Z going in. Okay, you can do either one. We'll show you. I won't show you. I'll use this one this quarter. Okay, but physicists use one, mathematicians use one. We also use this one. This one evolved, right? Everybody was doing 2D graphics first, and then they started doing 3D. And so, oh well, Z then had to be what was coming out of the blackboard at you, since you drew all your 2D stuff in the blackboard. This is how this one evolved. So when we rotate things, we typically think of rotating them. What's what we call the right-hand rule. Take your right hand and do the cupping. Look at the cupping direction of your fingers. That's the positive rotation, right? Negative is the other way. Okay? And we're going to be rotating things around the z-axis, the y-axis, the x-axis. We're going to be rotating things along everywhere. And if you don't see your friends doing this sometime this quarter, trying to figure out how to rotate things, right, you're not watching closely. Everybody's going to be doing this. We all do this. Right? Try to figure out how to rotate things by this being the positive angle of rotation, is the cupping direction of your fingers. Okay? So here I'm going to rotate this point, and let this angle be theta here, theta. I'm going to rotate it theta. Okay, around this point, theta radians around this point, or theta degrees around this point, if you will. And what I want to do is I want to find this point up here. What this point is equal to, x prime and y prime, is up here. Okay? Now, how you figure this out, I think, is you drop perpendiculars to everything in sight. This is geometry, after all, right? How do you do high school geometry? You drop or trig, you drop perpendiculars everywhere, and things kind of work out. This is what do I want to do? Oh, let's let this one be, I see, an even better way here. Let's let this angle here be phi, right? And I know how to calculate phi, right, because the cosine of phi, let's see, if this is r, this distance along the ray here, r doesn't change nicely as I rotate, right? R doesn't change as I rotate. So if I look at this, let's see, I think r cosine of phi is equal to x, and r sine of phi is equal to y, like that. And if I look at then x prime is going to be r cosine of theta plus phi, I believe, because I've rotated it theta. And y is equal to r sine of theta plus phi. And if I write this out, I get x prime is equal to r cosine theta cosine phi plus minus r sine theta sine phi. One of the two trig identities I think you have to know to do trigonometry correct. And when you look at this, you get x prime here is equal to, well, let's see, r cosine phi is x. Got me? Okay. And r sine phi is y, so this is x cosine theta minus y sine theta. And if I expand this one out here, I get r sine theta sine phi plus r cosine theta. No, that's not right. Let me try it again. That's cosine phi. R cosine theta sine phi. Is that right? I think so. And I get, looking, this is x sine theta plus y cosine theta. Okay? And now what I have to do is write down the matrix. So if I get xy 1, how do I get x prime and y prime out? Right? And 1. Then I take x, y, 1, and here's the matrix. It's not, you have to stare at it a bit. The matrix looks like cosine theta sine theta minus sine theta cosine theta 0, 0, 1, like that, I think. See it? Takes a little bit of work to get there. Go ahead.
I believe you mean r sine phi equals y.
Ah, thank you. Okay, so this is what we call r theta, maybe. There's a rotation, right, depending on the angle theta. Okay. Now, all fine and good, right? This is this comes out, I mean, this is kind of a cool matrix. You have to get the minus SIGN, the minus sign, in the right place. Okay, it's always a little tricky getting the minus sign in the correct place here. And as you'll see when we go to 3D, it'll be a little trickier. But it's a real simple matrix in general. So, you know, if I put theta equal to 90 degrees in here, this gets 0, 1, minus 1, 0, and gives me a matrix that rotates something 90 degrees. Okay, I had a question back there.
I've got a question about the scaling. You said we have to move it back to translate it back to the origin,
Yeah.
center of the object.
Yeah.
But what if we have a more complex object, not just a rectangle?
Oh, still the same thing, as long as the object's specified by some set of control points that can be moved. You're a little bit ahead of me. Let me keep going.
Okay.
Okay? Let me keep going. All right? So this one is rotation about the origin here. What happens if we want to take a point here, out here, x, y, and we want to rotate it with respect to some other point? Okay? What do? You should know the answer to this one real quick, right? Translate the origin, rotate it there, translate it back, multiply all the matrices together. You got one matrix that does the trick for you. Okay? Now, these three, translation, scaling, rotation, or what we call the elementary matrices in computer graphics, okay? There's some other things people use, but mostly we use these. And you'll see me stick with these most of the quarter. Okay, they're actually pretty straightforward to use. And what we do is we have a complete transformation system we set up to multiply, to set up and multiply 4x4 matrices times things. Okay? If you look out there in the C++ notes, there's vector classes, transform classes, everything out there that you can copy, use, whatever. Okay, when you write your code. So you know, you can use anything I don't want. I was having, when we did this in the early years, we were having too many students that were having trouble writing a routine that multiplied matrices. So we decided to write that for them. Okay, so there's all kinds of these elementary matrices out there, even including the camera transform. Okay, so here we have, you know, translation, scaling, and rotation. We're going to do a lot of stuff with just these three. They're all 4x4. Oops, they're all 3x3 matrices in this case. They all have this characteristic column, okay, which you're going to hear me harp about for a while. The column kind of has to be there. You can't deal with 2x3 matrices and multiply them. Doesn't work, right? It kind of has to be there, and we'll use this column when we get to the it'll stay 0, 0, 1 until we get to the camera transform and really implementing the perspective. Then we find that we'll start playing with this, right, to get this column back. Unfortunately, if you play with this column and it's not 0, 0, 0, 1, you don't get a 1 over here anymore. Okay, you get something else, and then that's where 4 dimensions comes in. Okay, then we'll start doing that. So let me do the easy part of 3D. Okay, so when you do 3D, you have a little. You have an X, Y, and a Z here. Usually a U, a V, and a W, and an origin. Okay, and I can just do my previous Blackboard stuff, taking a point P here. There's always a X, U, plus Y, V, plus Z, W, plus O type of an operation, right, in order to get these, to get from O to P. And we usually call, in this frame, we usually call the coordinates X, Y, Z the coordinates of P. Right? Standard stuff. And we usually write P as the standard thing here. Like that. Right? We just break it up into matrices so that we can deal with it this way. And if you notice, by the way, all my matrices were written on the right-hand side of these guys. Okay? And so they would kind of go in between these things, right? In between these two guys when I get there. But what we deal with in 3D is we deal with X, Y, Z, 1. Okay? And so we do translation in 3D. We get a translation matrix, right? This takes X, Y, Z, 1 and hits it with, right, if it translates by ABC, it's 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and A, B, C, and 1. Right? That's translation. It's exactly the same. Okay? It's exactly the same. There's scaling. Scaling does X, Y, Z, and 1 and multiplies it by, I think, A 0, 0, 0, 0, B 0, 0, 0, 0, C 0, and 0, 0, 0, 1. Okay? That one's easy too. Notice that this characteristic last column still has the 0, 0, 0, 1s in it, okay? And if we want to scale around a separate point, we translate that point to the origin, scale around it there, translate it back. Okay? Now what I'm thinking of here is that everything we do in 3D is going to be made up of points, right? That we can translate, scale, whatever. Hopefully they're going to be made up of, they're going to be characterized by a few points only. A line segment can be characterized by 2 points, right? And we can move it around just by moving both the endpoints. Right? A polygon is characterized by several points on the outside, or a square by 4, a triangle by 3, right? And we can move those points around, right? Turns out a Bezier curve or a Chaikin's curve also works because we move the Chaikin's points around, right, using these matrices, and we get the same, if we rotate the Chaikin's points, we get the Chaikin's curve back rotated when we get done, okay? And Bezier curves too, you get the Bezier curve back rotated, okay, if you just rotate the control points. So what we're going to do is apply these matrices to all our control points, okay? And if we have a scene, a huge scene containing millions of polygons, these matrices have to be applied to all of the millions of control points, okay? Which is why GPUs are a lot faster than CPUs these days, okay? In order to be able to do that. But when we come up, okay, so trouble is, right? What do you do with rotation in 3D? Okay, scaling, translation, that's easy. What do you do with rotation in 3D? Rotation is a little harder because how do you can't say I want to rotate around a point anymore, right? Because what's it mean to rotate something around a point? Okay, what you have to say is we rotate around a line or an axis, right? We have to rotate something around a line or an axis. When I do my 4D, a little bit of 4D here, in 4D you have to rotate around a plane. Now, don't lose any sleep over this tonight, okay? But we don't have to worry too much about that. But there are classes in the math department you can take that discuss that, okay? But in 3D we have to rotate around an axis, okay? And so take a point and a vector sticking out of it. We can think of that as an axis. And we want to rotate around that. Well, there are plenty of axes we can think of, okay, to rotate around. Any of the set of vectors, right, and points will work to rotate around. So all of a sudden we've gone from something where we had just nice, simple rotation in 2D with a few points maybe we could rotate around. We could just shift to the origin, rotate there, shift back. Now we've got all these potential lines that we could rotate around, and we have to figure out how to rotate around them, right? And so all I'm going to do today, finishing up, I'll do the real one tomorrow or Friday, okay? But all I'm going to do today is say, well, there are three axes that we know a lot about, right? Number one, the x-axis, the y-axis, and the z-axis. You know, if our frame is the standard frame. We know a lot about those, and so let's rotate around those. Let's figure out how to rotate around those axes, and maybe we can combine that operation into, we can rotate around about any axis. Okay, and that's the strategy. We're going to build up those three first, and then we're going to be able to rotate around any axis later. Okay, and it's not too hard. So it's really pretty easy to think of these things, because if I'm going to rotate around one of these axes, the y-axis, let's think of the z-axis coming out at you. If I'm going to rotate around the z-axis, okay, things are going to look pretty much like cosines and sines again. The only thing I have to convince you is if the z-axis comes out the board at you, right, and x and y is in the board, if I rotate a point around the z-axis, can I convince you the z-coordinate doesn't change? Okay? You should be able to see that. If I rotate around the z-axis, the z-coordinate doesn't change. If I rotate around the y-axis, the y-coordinate's not going to change, right? If I rotate around x, the x-coordinate's not going to change. So only two of those coordinates are going to change, okay? And so it's not too hard to see that if you do rotation, and let's say x-axis, let's do z-axis first, by theta, if I rotate a point around the z-axis by theta, right, it's going to look like x, y, z1, right, times this matrix, right, which looks as follows. Well, I can start writing some things down immediately. This column 0, 0, 0, 1, I know that. Okay? As I said, as I rotate around the z-axis, the z-coordinate doesn't change, right? So this thing has to be 0, 0, 1, 0, right? Third coordinate only picks up the z-coordinate, so it doesn't change. So the only change is going to happen here, and guess what? You're going to get that as your matrix. Okay, this is rotation. It looks almost exactly like the other one, right? Except it just keeps the z value constant. Okay, it looks almost exactly like the other one. So this is rotation around the z-axis. Now, if I do a little bit here, let me, let's take a point here that I know something about. How about the point 1, 0, 0? And let's rotate it 90 degrees around the z-axis, okay? Now the cupping action of my fingers really is important here because I got to lay the thumb now along the axis that I'm rotating around, okay? I'm going to lay the thumb along the axis that I'm rotating around, then the cupping direction of my fingers is going to be positive, okay? And let's make sure this is going to work. I'm doing this for purpose because one of these doesn't work. Okay, the minus sign here happens to be in the wrong place. Okay, I'll figure it. I don't know which one. I'll figure it out as I go along. Okay, but here we go. So let's rotate this around. So we take this point, which is 1, 0, 0, 1. Add the 1 on there. And I take this matrix right here with theta equal 90 degrees, basically. Pi over 2, which means cosine is 0, right? Sine is 1. Right, so the matrix becomes 0, 1, 0, 0, minus 1, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And if I multiply these guys together, I get blah, blah, blah. I get 0, I get 1, I get 1, and I get and I get 1. Okay? No, that's not right. Let me try it again. There should be a 0 there, right? Too close to the board here. Okay? So 0, 1, 0, 1, and this is the point up here, right? So it did what it was supposed to. Okay, rotated at 90 degrees. All right, let's do the other two. I can finish these off quick. Okay, here's, if I rotate around the x-axis, theta, right? I take x, y, z, 1, and my matrix better look like last column 0, 0, 0, 1. Now if I rotate it around the x-axis, the x value has to stay the same, right? So the first column better be 1, 0, 0, 0. Keep the x value the same. And then I do my cosine sine thing with y and z. So it looks like 0, 0, cosine theta, sine theta, minus sine theta, cosine theta, 0, 0, like that. And if I take this thing here, and I take a point, let's take this point up here, 0, 1, 0. If I rotate it around the x-axis, so you put your thumb along the x-axis, get the cupping direction of your fingers, rotates at 90 degrees down there, right? I should get a point on the z-axis when I'm done. And if I do that, here's the point 0, 1, 0, 1. Add my 1 here. And I've got this matrix now, 1, 0, 0, 0, 0, 0, 1, 0, 0, minus 1, 0, 0, 0, 0, 0, 1. Because cosine is 0, sine is 1. Okay? If I multiply these guys together, I get 0, I get 0, I get 1, and I get 1. Okay? And this is the point on the z-axis, as promised. Okay? Kind of makes sense. So the one that's going to fail is the next one. Okay? And this one is r around the y-axis, theta. If I do this, x, y, z, and 1. Fourth column is 0, 0, 0, 1. The second column has to be preserved, 0, 1, 0, 0. And now I do my cosine and sine thing with x and z. So I get cosine theta, sine theta, 0, 0, minus sine theta, cosine theta, 0, 0, like that. And if I take, hope this works, here's x, y, z, and if I take a point, let's take this point here, 0, 0, 1, here, on the z-axis and rotate it around the y-axis, sticking my thumb up, right, cupping direction, 90 degrees around the y-axis gets it to there. Okay. Let's see what I get. That's the point 0, 0, 1. I'll add my 1. Cosine is 0, sine's 1, so that's 0, 0. Oops, let's try higher. 0, 0, 1, 0, 0, 1, 0, 0, minus 1, 0, 0, 0, too close, 0, 0, 0, 1, like that. And when I get out, I get minus 1, 0, 0, 1, right? And you say, oops, right, not good. What happened was it went the other way, okay? It went this way. And so in order to preserve a right-hand rule, right, so that everybody can keep doing this all the time, honestly, you go to a graphics company, 3D animation company, you see people doing this all the time, okay? Once you do, to preserve the right-hand rule, what we do is we switch this guy up here. Okay? And if we do that, in the example, it switches him up here, and that goes away. Okay? And it goes to the right place. So, you know, I've covered a lot for you today. I did frames. I did, you know, these things to show you where we have to stick this 1 in here, right, because it picks up the origin in our frames. You know, generally I've been working with the x-coordinate, y-coordinate, z-coordinate, but of course our frames could be any vector, any combination of 3 vectors here, and they all work. Everything works just fine with this. We went through translation, scaling, rotation in 2D, and they were really pretty easy to do. And then we went through translation, scaling, and rotation in 3D. A little harder to do, okay? But we really haven't come to the really cool question yet, which is, given any axis, how do I rotate around that axis? What's the matrix that I rotate around that axis? And it's actually pretty simple to do. What you do is you translate your point down to the origin. We can figure that one out. Now what you do is you translate your vector, move your vector until it becomes one of the ones we know, right? And you can do that with these matrices. You can move that axis down until it becomes one of the axes that we know. Once it's one we know, rotate. Now put it back, right? Right. So there's going to be 7 matrices in a big, huge mess when we get done. All right. Moral of the story, though. Moral of the story. Come away from this lecture thinking you move things around with matrices, right? 0, 0, 0, 1 in the 4th column, always. Okay, and it's easy. And plus, Joy has a class out, C++ set of classes out there you can use when you write your programs. So you don't have to write all this stuff down. Okay.